given by just symmetric products of the family Y. So, and the velocities here are given by what? Can you, any expectation? So this is new to us. This is new to us due to the special mechanical structure. Accelerations are given by symmetric products, which are a special type of Lie brackets, but particularly they are, Lie brackets on this form. Okay, so if you want to get an acceleration, go and do symmetric products all over and over again. What about the velocities? They're just Lie brackets of these guys, right? So this is actually a theorem, I forgot. This is a theorem. That the Lie algebra of the family of vector fields, that this special class, can be decomposed into accelerations and velocities. That all the accelerations are given by the symmetric products, velocities are given by Lie brackets of these guys. So this theorem can help us to characterize controllability for mechanical systems, and we need just to modify a little bit the definitions that we had before for controllability. So consider our definitions here for controllability and reachable sets. So we have sigma mechanical, that is Q nabla or G defined by the covariant derivative, a way to do the derivatives which is equivalent to the Riemannian metric, which is equivalent to the kinetic energy. What else? We have set of admissible velocities or the non-harmonic constraints. We have your family of control accelerations and the control set. And we have, this is the equation of motion, is nabla gamma prime is summation j 1 to m yj of q uj. This equation that we called 2. And we have a point q naught and some velocity in the tangent bundle. We will consider the point that is with zero velocity from starting stationary. Can we do things around, which is the hard case. The hard case not in analysis, actually this is easier in analysis, but the hard case in actuation itself. Sometimes we call this point as 0 q naught. It's in the tangent space, it's the zero element in the tangent space at q naught. Anyway, it's just a notation. It's some q naught in the configuration manual with zero velocity. So this is zero initial velocity. Okay, now we can define the reachable set, or sigma. Now it's called sigma m. Now sigma m, I can get velocities, I can get positions. So we have two reachable sets actually. Here, if I'm talking about both positions and velocities, so I'm interested in the entire state space, I will call it sigma m comma tq in the entire state space, position and velocity, from q naught and in time t. This is what? This is every gamma of t such that gamma is a map to q satisfying the equation 2 for all t with some admissible controls, and gamma of 0 is your initial point, gamma prime of 0 is 0 vector. Okay? So you just integrate your equation all the set of points that you can get, simply. This is well, let me define first in Q, okay? So this is in Q, this is the set of positions. Gamma of T, just gamma, the set of positions, gamma in Q. And then I'm going to do exactly the same, R sigma M, comma here, TQ. This is just gamma primes. Everything is the same. Okay? Positions in TQ, the understanding that TQ is positions and velocities already. And from these we define in the thing that is at most time, so Q naught at most time T. This is the union over T from 0 to large T, the reachable set in Q of Q naught and T. And likewise you can define R sigma M TQ in at most time T. You just do it. Any questions about these definitions? They make sense to extend our definitions just to have difference between position and velocity. Sometimes we will be able to achieve all positions and velocities. Sometimes this is a hard requirement. We'll just focus on positions. Velocities are harder to get because why velocities are harder to get? Because to get a net shift in velocity, it means in the limit, and you want to do it as fast as possible for all t, it means that you are able to achieve an effective acceleration. And like I said, acceleration means like it's a force. So creating a force is not that easy. Most of the time we will not be able to achieve that this guy, the reachable set in the tangent bundle position and velocity has an empty in t. Most of the time we will not be able to achieve that. So this actually leads to the definitions of accessibility. So sigma is accessible from Q naught if there exists some time such that, what, can you tell me the definition?
The interior.
The interior of the reachable set. We're talking about the entire sigma, this is sigma mechanical. So this is the entire tangent bundle from Q naught in at most time t. This should be non-empty interior. But you can say that actually here, you can say that why? Because from the beginning, for the definition of sigma, there are some directions in the tangent space that you cannot achieve from the beginning by the very definition of sigma. So here we're interested in the interior with respect to d. Okay? Yeah, because I mean it doesn't make sense to try to get all the acceleration when you know that you cannot go in these directions anyway by constraints, physical constraints. Okay, so that's okay. Sigma is accessible. Here we have an updated definition or a special definition for mechanical system. It's called configuration accessible. So the last definition was not new actually, except for the thing D. Configuration accessible. What's that? Then I don't care about velocities, but I care just about positions. Okay?
So,
yes?
here's a question. So the definition of the reachable set for the tangent bundle, it should be an ordered pair, right? Like the positions and velocities?
Yes. But
we're not talking about velocities only, right? We're talking about
with the understanding that if I'm talking about velocities, I implicitly talking about positions as well, because there is no meaning of velocity without specifying a point, right? You say this velocity lies where, well, it lies in the tangent space at that point, so it comes as a pair. So this is actually related to the how do you define a vector field in 3 dimensions? Well, components-wise, we give 3, right? But the vector field is actually a map from the manifold to the tangent bundle. So ideally, strictly speaking, this guy should have 6 components. So y at a point should have 6 components. But the first 3 are trivial. These are just the point. And these are the velocities which we care about. So this is just a technicality. Yes, when we say velocity, we implicitly mean it's a velocity at a point. Okay? So what do you mean by configuration accessible? So here, if there exists T such that I'm just focusing on the reachable set, in the Q space. It's not in the tangent bundle, just the configurations. These guys should be non-empty in Q. So the interior is non-empty in Q. Okay? This is the empty set. Okay, so just a new concept called configuration accessible. And we can do the small time local controllability. Sigma M is small time locally controllable from this guy, yada yada, if there exists T greater than 0 such that. What? Can you tell me the definition? Small time local controllability implies what?
X naught is for Q
Yeah.
in the interior.
This guy, Q naught, and the 0 vector is in the interior of the reachable set. Again, this is the interior over D, and an analogous concept, sigma M is small time locally configuration controller. Configuration controllable. Everything is the same. If the point just Q naught is in the interior of the reachable set in the Q space. Okay. From these definitions and the theorem that we have that, remember, for all analytic systems, the Lie algebra is your capability. This is your utmost things that you can achieve. Well, we're saying that your capability here with respect to net changes in velocities or effective accelerations are symmetric products, and net changes of positions or effective velocities are Lie brackets of them. So based on this theorem and these definitions, we can say the following. It's another theorem that sigma and analytic sigma, this is for analytic systems to have sharp conditions if and only, is accessible from Q naught and 0 if and only if what? Well, we need to cover all the possible accelerations. So the infinite symmetric product of this family y at the point is what? Can you give me an expectation? What do you expect? What do you need to cover?
The tangent bundle
No?
sub.
This guy, right? Yeah, the subspace that you. This is your entire thing, right? The admissible velocities. I need to cover the admissible velocities. Remember, anything here is a net change in velocity. And if you do it fast, it's an effective acceleration. So I took care of the velocities, but for the positions, I need to make sure that the Lie bracket of these guys, if I cover them at Q naught, covers what? Covers what?
Tangent manifold. The tangent to the manifold at that point.
Yeah. Which is isomorphic to Rn. Okay. What about just focusing on the configuration axis? If and only if what? Configuration accessible, I'm interested just in here, and I may not have covered the entire D, so whatever I got from here, I'll do the Lie brackets of them. So Lie infinity of sim infinity of your family of control accelerations y's, this should cover the tangent space at q naught of your q, which is isomorphic to R. Okay? So we're gonna just play with symmetric products and D brackets as usual, and let's have an example. Any questions so far? Any question? Okay, let's have this example that yes.
Yeah.
Sure.
So symmetric products are, in fact, they are bad brackets, right?
Not necessarily. We will talk about this in a minute, because they are bad brackets if they are y1 with respect to y1. But if y1 with y2, it's not a bad bracket, right? Yeah, it's a very good point. It's a very good point. Let's have this example. Remember this was, I think we considered it before. They call it in literature hopping robot. And we have just here like a body. Fixed is just allowed to rotate, so it has an inertia I. And we have here a robotic arm that can extend. At the end of this guy, we have a mass M. So this is a length L of T that can extend. We have two angles, theta for the body, and psi, the relative angle between the body and the arm. We analyzed this problem before from a kinematics perspective, so ignoring the dynamics, respecting the kinematics, and we analyzed it in the sense that can we get all possible configurations, theta, L, and psi? Is it controllable in that space, right? But in order to do that, you have to, we're going to neglect the dynamics, that's fine. But what is the outcome of the dynamics? You need to respect it. What was the outcome of the dynamics that we took for granted? We said, well, for this dynamics, actually, theta is an ignorable coordinates. So we have a conservation of momentum. We treated this conservation of momentum as a non-holonomic constraint, although it's not, okay? As a non-holonomic constraint, so we got what we call kinematic system. So just instead of kinematics, little change of positions equal velocities. Subject to that non-holonomic constraint, so it removes the ability to generate one velocity. Typically we have three velocities, but if you have a constraint, then you're going to remove one. So we have freedom to generate L dot, psi dot, but theta dot will be dependent. And using these two vectors, we analyze controllability. The system was controllable.